Hello everyone. In this lecture, let's talk about lag value in autocorrelation. When we analyze time series, we often talk about values that our time series took in the past. For example, 1, 2, 3 steps. These are known as the lag values. And lag is the number of interval between two observations. So the lag between the current and previous observation is just 1. And if you go back one more interval, the lag is 2, and so on. And lag plot is very useful plot to explore this type of relationship between each observation. And lag plots can provide answers to the following questions. Is data random, right? Do we have any outliers? Do we observe any seasonality? Is there any autocorrelation? And also, what is the suitable model for our data? Creating lag scatter plot, as the lag plot is the type of scatter plot, allow you to check for randomness. And random data will spread evenly, both horizontally and vertically. And if you cannot see a pattern in the graph, then more likely your data is random. However, if your data shows some sort of pattern, particularly a linear pattern, it suggests that you have autocorrelation, you have a trend. So the positive trend would be going upwards. Negative trend would be going downwards. Now, if you find the data that look like a ball in the middle, it suggests a weak or no relationship. Also, look how tight the points are together in your linear pattern. The tighter the data is clustered around the diagonal, the more autocorrelation is present, right? And the perfectly autocorrelated data will cluster in a single diagonal line. Lag plots also useful to check for outliers. Can you detect 3 outliers or 4 outliers actually in this figure? So these are points with extremely high or low values. Another very useful feature to check is seasonality. Seasonality is a periodic fluctuation in time series that happen at regular periods. It could be season, hours, weeks, minutes. Don't confuse them with seasonal variations, the changes in just particular season, which is very easy to detect. Here we're talking about seasonality. It is unknown time period. It's hard to detect, and with the lag scatter plot, we should be able to observe the periodic fluctuation. Seasonality can cause issues actually interpreting time series data. How do we determine what model is best fit for our data? Actually, the shape of lag plot can provide us clues about underlying structure. So if we have a linear shape, the plot would suggest that we have autoregressive model. So that would be probably our best choice. Some sort of elliptical. An elliptical plot would suggest that the data comes from perhaps sinusoidal model. In the last couple of slides, we were talking about lag plots, right? When we had a y and y minus its lag value. Now we're going to switch and start talking about autocorrelation, which is serial correlation. Autocorrelation is correlation of time series with delay copy of itself, and it's a correlation coefficient. And the correlation associated with the lag plots is called autocorrelation function. Autocorrelation function is a Pearson correlation between observations at a different lag. And you can look at the formula. So ACF, abbreviation for autocorrelation function of given lag. It is indeed correlation between YT and YT minus lag, which is, if you remember Pearson correlation formula, we have covariance of x and y, and we have standard deviation of x and y. So here we plot covariance of x and x lag value and standard deviation of x and its lagged value. When the autocorrelation is used to detect non-randomness, with the question, is my data random? Typically, only lag 1 is used. But for determining an appropriate model, many lags are plotted. So that's the difference. The plot actually that represent autocorrelation function is called Correlogram. Each bar in this plot will represent the size and direction of the correlation. The bars that you see with positive or negative direction, they extend across the confidence interval window, sometimes marked with the red or blue or dotted line. So the bars that extend go beyond this confidence interval are statistically significant. So that's what we need to look for while analyzing ACF. In this specific example, we have example of random data. What you notice right away, those bars do not cross significance level. This is important. Random data clustered typically around 0. There's no significant lag. So you can state with high confidence that data represented in this plot is random. Another thing to remember is also from what you've learned in the past about Pearson correlation, that the range for coefficients is between -1 and 1. So -1 will be negative correlation, 1 will be positive correlation, and 0 will be no correlation. So when we talk about random data, we refer to it as a white noise, independently distributed, uncorrelated observation with a constant variance, right? They all clustered around 0. What about trends, seasons, and stationarity? How can we detect that from ACF plots? Trend, if you look at the plot on your right, will show a slow decrease. So you notice there's a slow decay. Shorter lags typically have large positive correlation between, because observations closer in time, they tend to have similar values. You notice all these bars are significant. If there's a seasonal variation, you notice you can observe seasonal spikes. In this case, the data of air tickets for passengers. So the spike is around 1 year. The lags are year lags. So there's spike at 1. So seasonal spikes will be superimposed on this pattern. All right, stationarity, where there's no obvious trends, no seasons, and the feature for autocorrelation function will be rapid decline. So if you deal with data, stationary data, you'll notice an ACF will be showing rapid decline past the significant level. If you're dealing with the trend time series, or time series with trends, non-stationary time series, the decrease will be slow and will continue to be significant for a long time. All right, that's the major difference. One more thing to mention is lag 0 is always 1. The reason why we use lag 0 is to help us compare values of other autocorrelation relative to, let's take it as a theoretical maximum of 1. So it will be just comparative. Our key takeaways are, we have lag plots, autocorrelation plots. They help us determine what type of data we have, whether data is random, whether we have correlation, if we have outliers. And autocorrelation tells us the degree of similarity between time series and lag versions over some time intervals. And these are linear relationships. Keep in mind, if your data does not have linear relationships, you will not be able to display it through autocorrelation. Also keep in mind that we have certain correlation coefficient, +1, -1, to look for, or 0 to detect the type of correlation. And you can use these plots to measure, for instance, how much influence past prices may have on a future price. It can help you determine also if there's a momentum factor that would be at play with the, in case of financial analysis, with a given stock. All right. In our next lecture, we'll discuss about time series decomposition. See you soon.